Hello, everybody. Welcome to this week's Astro Coffee Hangout. My name is Tony Darnell, as always. I'm from deepastronomy.com, and today's hangout we're going to be talking about galaxy alignments in the distant universe. Astronomers using the Hubble Space Telescope have been looking at, I believe it was a number of galaxies, 65 galaxies, and they are trying to determine how these galaxies line up. And we're going to talk about what that means, even to be a lined up galaxy versus an unaligned galaxy, and maybe as well as the cosmological support of it, or the cosmological significance of all of this stuff. So I'm very excited about today's hangout, and I hope that you will enjoy it as well. As I get started, let me introduce my co-host. Her name is Dr. Carol Christian. Hi, Carol. Welcome.
Hello.
Hi. So you are at your base of operations, it looks like now. So
yes.
You're back from your travel, and you were doing some courses last week, I guess. How'd that go?
It went very well. We're doing some presentations with assistive technologies of astronomy content for the visually impaired, blind and visually impaired. And the students were very bright, very enthusiastic, and it's a career-oriented program. So it went very well.
Oh, good. Okay.
Very pleased.
Well, while I have you up, why don't you give our viewers a intro into these hangouts and who sponsors it and make all this possible?
Sure. So a while ago, we had this, probably, 2 or 3 years ago now, we had this discussion about how astronomers and scientists in general very often have within their research institutions and their universities something called science coffee. It can be daily, sometimes it's just once a week. And they get together and informally talk about the research that they've read about and they're interested in. And so we had this idea, boy, these conversations are pretty interesting. Maybe we could invite the interested public in to share this and dialogue with us about the research. And then we said, well, do we really want to have, for example, Tony and I talking about something without getting the actual researchers who were doing the work to tell us about how they decided to do the work, what they did, and what the conclusions are. So that is how Afternoon Astronomy Coffee was born. It's like science coffee, and we invite you into dialogue with the actual researchers and often engineers who are doing the work or building a telescope, something like that. So this is co-sponsored by the American Astronomical Society, so that's the astronomer side, and the American Astronautical Society, which is the engineer side. And we're very grateful that they are supporting this, and we're glad to have their members on board our Hangouts.
And I just want to give a shout out to Carol, because I am glad she's the one who comes up with these great topics each time. She works hard to make sure that we have something interesting to talk about each week. So thank you, Carol. I really appreciate your efforts too.
Well, my colleagues are doing all kinds of interesting stuff. So.
That's true. They really are. So, okay. Well, let's go. The only thing I would add to what Carol said is that we are streaming like mad these days. I'm on YouTube right now, Twitch, Facebook, and also on Periscope, and I'm monitoring the YouTube chat on Twitch and YouTube. And Carl has Facebook and Twitter covered for us. You can also use the hashtag AstroCoffee to interact. We hope you'll talk with our guest today and ask him some questions about the research he's doing, which brings me to that topic: galaxy alignments. Do they line up? And if they do, are they random? And if they're random, why? Or do they line up? And what does that even mean to be lined up? Lined up with what? So we're going to be talking about all of that. And my guest today is, let me just get him pulled up here. His is Dr. Michael West. He is let me get myself out of the way. There we go. And Dr. Michael West, there he is. He's the deputy director of science at Lowell Observatory. Hi, Michael. Welcome to our hangout.
Hi, Tony. How you doing? Hi, Carol.
So we want to find out. Let's give us an introduction into what your paper is about. By the way, the paper is we have links. We have links to the description. In the description box, I have links to the press release from Lowell Observatory. We also have links to the Nature paper that we're going to be talking about. So please follow along with us if you want to download that paper and ask questions from that. We also have we have Michael's Facebook page linked to in the description box. So please check out what he's doing. He's doing a lot of really great work. So Michael, if you wouldn't mind, give us a little intro into your paper. What were you doing and why?
Sure, thanks, Tony. Well, if you think about it, when we measure properties of galaxies, we look at sizes and shapes and luminosities. And one of the most basic properties is a galaxy's orientation in space. And for years, astronomers assumed that galaxies, like snowflakes, were randomly oriented, right? There's no preferred direction or anything. But over the past few decades, there's been evidence that some galaxies, in particular the biggest galaxies in the universe, these giant elliptical galaxies that we find at the centers of galaxy clusters. Galaxy clusters are sort of the cities of the cosmos. They have hundreds or thousands of galaxies all sharing the same space. And the biggest ones in these clusters seem to know about their surroundings. Their orientation seems to point in the same direction as the elongation of the cluster in which they reside. And so this is well established for nearby galaxies today. But we were curious to look back into the past. And of course, Hubble Space Telescope is a great time machine. As you know, the further away you look, the further back in time you look. And so we wanted to see if we could find similar galaxy alignments in the early universe. So we used Hubble to look at 65 very distant galaxies and their host galaxy clusters to see if the galaxies also knew about their surroundings. And what we found was that, yes, they did, as far back as 10 billion years ago, right? So that's looking back 2/3 of the way back to the Big Bang. These galaxies somehow already knew that they should have certain orientations with respect to their surroundings. And we think that has all sorts of clues about how these galaxies might have formed and the timescales over which they formed.
Okay, so and you said this was back to, would you say 10 billion years? Was that the most distant, or was that where basically all of them were?
That's the most distant one. We looked everywhere back from about 2 billion years out to about 10 billion years back in time.
Okay, so were these galaxies? So what were the? So were the galaxies were they more or less the same kind of galaxies, or were they different types?
Yeah, so the galaxies we looked at are actually some of the biggest galaxies. They're the biggest galaxies in the universe. I don't know if Carl can put up one of the images of the cluster MAX J0416. This is an image that will show you one of the clusters that we studied.
Okay.
And like I said, these galaxy clusters are just these enormous systems. They're like cities. They're these enormous systems of galaxies all dancing around each other because of gravity's tug, immersed in pools of dark matter. There you go. So this is one of the galaxy clusters that we studied, MAX J0416. This is a cluster that we see as it looked about 4 billion years ago. And you see that there are many, many galaxies in this image, a few large galaxies. What the blue shows here is a map of what we believe is a distribution of dark matter in this cluster. And you can see the cluster looks quite elongated to your eye. The way the dark matter is mapped is through gravitational lensing. This is the bending of light from more distant galaxies as it passes through the gravitational field of a cluster like this. And so what we did was we looked at clusters like this, and we see that it's quite elongated. We can measure the orientation of this elongation. And then we look at the orientations of the individual galaxies within the clusters to see if they share that same elongation, that same orientation in space. If you could put up the next image that had the galaxies with the red lines through it. No, not that one. So that's yeah, there you go. So for each of the individual galaxies in these clusters, we measured their orientation in space. And we found that most galaxies, in fact, are randomly oriented. They don't seem to know anything about their surroundings.
So hang on, these are the galaxies within the MAX cluster that were local to each other, and they don't show any preferential alignment at all. They're just kind of thrown around in there.
Right. This is a different cluster than the MAX cluster,
but
yeah, that's the idea. So each of those galaxies has an orientation. It's elongated in a certain direction of space. We can measure that using Hubble. And then we found that, sure enough, most galaxies do have random orientations. They don't seem to know about their surroundings, with one exception. And that's the biggest galaxies, these super giant galaxies that reside usually at the center of these clusters. These are beasts, right? These are, these could gobble up, many Milky Way galaxies. These are the biggest galaxies in the universe. And they know about their surroundings. They share the same elongation as the cluster in which they reside.
Okay, wait a minute. These are the largest galaxies in the universe, and they have the characteristic color and shape of ellipticals, right?
Right, they're elliptical galaxies.
They're elliptical galaxies. Now, elliptical galaxies, when I look at them, just look like a big blob, a big ball of undefined structure. How do you find a plane of rotation or any kind of thing to say it's oriented this way in a big sphere or in a big blob?
That's a great question. They're not rotating, but they are elongated. And so they're not perfectly spherical. We can measure an ellipticity, how flattened they are, how elongated they are, and a direction to that elongation. Is it up and down, east and west? And that's what we do. So even if you look at most of the galaxies in this image, it may be hard to see over the internet, but most of them are actually elongated to varying degrees. And that's what we measure. We measure the shape and the orientation of that elongation.
Carl, can you zoom in just a little bit more where maybe there's like 4 lines or something in there? Okay, so that's good. That's perfect. Now look at this. Now we have here a bunch of lines that are drawn. I can see some of them, like I can see a couple of them. I can see the structure you're talking about. But I just want to dive into this a little bit because I want to know how you do it. If you look at that one sort of semi-horizontal line to the center, in the center left, and then you see right next to it this vertical line almost, right directly adjacent to it. What do you do to get that line drawn? How do you do that? To me, and first of all, also, how do you separate it? How do you separate one galaxy from another? That looks incredibly hard.
That's a great question. So doing this by eye would be extremely difficult. Never trust a human, right? So what we do is there you go. We run software to actually map the distribution of light in each galaxy, and it tells us very robustly what is the shape and orientation of that galaxy. So there's not to say there's no human involvement, but it's an objective way of measuring this. So there's a program that we use called GalFit, and it's been written by some astronomers, and it takes any galaxy you like, and it measures how the light is distributed within it, and it gives you back information on shape, orientation, how concentrated or diffuse the light distribution is. You get lots of information from this, but it's an objective software program, so it doesn't involve me looking by eye and saying, "Oh, yeah, it looks like this." It does it for us.
Okay, just because I'm going to get nerdy for a minute, because I know some of our viewers are interested in astronomy software. Is GalFit written in Python?
No, it's not actually. There may be a Python version out there.
But it's in C?
Yeah. So it's actually quite straightforward. You can get it for free. There's a link. The astronomer's name is Peng. I think it's at Caltech, if I remember right. But it's available for free on the internet. And there's multiple versions of programs like this out there too. Even in IRAF, which is well-known astronomy reduction software, you can run a routine called ellipse. And ellipse will, as the name implies, fit ellipses to the distribution of light in each galaxy.
Okay.
And it will give you information like the shape and the orientation, that sort of thing.
So using computer software that you automatically run on these images, you're able to get these alignments from amazingly featureless looking things. And these are the oldest galaxies in the universe. Now, these are 10 billion. This is when the universe was 3 billion years old, right? About 3 or 4 billion.
So these aren't the oldest galaxies in the universe, but these are galaxies as we see them as far back as 10 billion years ago.
So as early as 3 billion years after the Big Bang, elliptical galaxies were around?
Oh, yeah, sure.
Wow.
Even earlier.
Wow, that's amazing.
Hubble has found galaxies at much greater distances, much earlier epochs even, and we we didn't have the data to do our particular study with that, but certainly Hubble's found galaxies at much earlier epochs even.
Okay, so these were what you found. I'm sorry I dove into that probably a little more than most people wanted to know, but it was interesting to me, so I wanted to learn more about it. This is what you see when you look at the local galaxy clusters and their alignments. Now,
Right.
let's go back. So go ahead and complete where you were going with this. When you look, what did you do? Pick certain galaxies out of this cluster to compare with others, or
So no, we take each galaxy and we compare it with the orientation of the cluster in which it resides. So the image that we showed earlier.
oh, so the entire cluster also has an orientation.
Exactly, and it's elongated. And you can see that in that first image. That cluster, the MAX J0416 cluster, I don't know if you can bring that picture up again, Carl, is actually quite elongated.
Yeah, go ahead and bring that up and then maybe zoom it back out. I'm sorry, Carl, I got you working today. But
That's why I'm here.
but yeah, I wanna see what that looks like in the bigger picture. I love deep fields, so in galaxy clusters, so it's just a pet thing.
Yeah, and this, by the way, I should mention, is one of the frontier fields,
Yep.
and it's one of the clash clusters.
That's right, and we've
too.
talked about frontier fields before, folks. They just finished that survey, I think, didn't they, Carol?
Yes.
Taking the data?
And people can get these images too by going to typing in Google, hey Google, what about frontier fields? And you can get the data.
Show me
if
some
you
frontier
want to
fields.
do galaxy alignments, you are welcome to it.
Yes.
You can. And the image is gorgeous. It's
Yeah.
really nice.
Yeah, it's one of the greatest uses of the Hubble Space Telescope since the deep field itself, in my personal opinion. So anyway, okay, so Carl has that back up, zoomed out. Let me get myself out of here and make that.
Oh wow! I see the alignment line.
Yeah, and okay, so
So
forgetting a minute the dark matter stuff, which I want to get to in a minute, but the blue halo. Wait.
So that's the optical image of that cluster.
Oh, okay, all right. So we'll use that then.
This is without the dark matter.
Yeah, okay,
And this is with it.
Yeah, that's nice
Just
with the
kinda
alignment
give an
arrow.
example.
okay.
Yeah, with the alignment.
Okay, so there's an axis of all of these galaxies, right?
Exactly. Well, there's an axis for their distribution for the cluster itself. And then we said, okay, does each of the individual galaxies, does their orientation somehow reflect the overall orientation of the cluster? And the answer is, for most galaxies, no. But for the biggest one, and it's only the biggest one in each cluster, yes, it shares a similar orientation as that line that you see, for example.
I feel like you need to say that again. For the biggest galaxy in the cluster, it shows an alignment with the cluster itself?
Exactly.
Okay.
And all the other galaxies don't. And so to us, that says that there must be something special about these galaxies. Not only are they the biggest galaxies around, but somehow they know about their surroundings, right? And to us, it's kind of remarkable that, these same galaxy alignments that we see today for nearby galaxies, we see as far back in time as 10 billion years ago, right? So whatever created these alignments did it very quickly, right? So to us, that's pretty remarkable. And in fact, the alignment strength is very strong, even at these early epochs. So it's giving us some hints.
Well, wait a minute, though. It's not that strong because it's only with the biggest galaxy. Not the. Why?
sure.
If it were super strong, it wouldn't. Or stronger, wouldn't the other galaxies also align up?
Oh, absolutely. You're right. I just meant for the biggest galaxies, the alignments of the biggest galaxies that we see 10 billion years ago seem to be as strong as the ones that we see today. But you're right, the other galaxies don't seem to line up. They don't seem to be aware. So to us, it seems to say that these biggest galaxies, in some ways, galaxies are like people. We're products of our environment. And these giant galaxies are very sensitive to their environment because for whatever reason, and there's different theories, their orientation reflects their surroundings, their environment, and we want to figure out what caused that.
So I did want to ask if there is velocity information about these clusters. Anyway,
that's a great question. So there's redshift, there's velocities measured for many of the galaxies in the cluster. So that's used to measure the mass of the cluster and things like that. In some cases, that's how we decide if a galaxy is a member of the cluster, because when you look at an image, some of those galaxies are in front or behind.
Right.
In other cases, we use things like color information to figure out if the galaxy was actually a member of the cluster.
So for distance and membership, but what about rotations?
No, we don't. No, we can't. These are too far away. They're really faint. It would be really difficult to do.
To do what?
It's actually,
Measure their rotations?
yeah, and again, most elliptical galaxies don't rotate, right? They're held up by. It's like what keeps a balloon blown up. It's the motions of the air molecules inside the balloon. In a sense, this is what keeps an elliptical galaxy blown up. Is the motions of the stars inside of it, and they're not rotating; they're just moving in different directions.
Okay, Alexander Reynders has some good questions. Let me get to a couple of them here. He's asking, and these are they have to do with what we're talking about here. He's asking, are these alignments coincidence to Earth view? And then he follows up with, what orientation from other views in space? So, is there a reference point here? Are you with any of these alignments?
Well, if you looked at them from a different perspective in space, you would presumably measure a different orientation on the sky, depending on where you are. But we're always measuring a relative orientation. So what's the relative orientation of the biggest galaxy compared to the cluster of galaxies in which it resides? And that, I mean, there are projection effects because we're seeing these galaxies projected in 2 dimensions on the sky. But in principle, it doesn't matter where you look at it from. If you were somewhere else in the universe, you would see the same sort of alignments.
All right, and John Suffol's asking, is the largest galaxy placed in the center of clusters? So you said this large galaxy. Is the largest galaxy in the middle?
That's an excellent question. That's one of the things we're actually trying to look at. 99% of the time, yes. In fact, that's probably what we think makes them special, the fact that you find them at the centers of these clusters. You know, if there's one space in the cluster that's kind of unique, it's the very center. I sometimes think of it as like the sort of gravitational focal point. Anything that falls into the cluster is heading towards the center, and there's a big galaxy sitting there. Maybe that's how they're born. So yes, in almost all cases, these giant galaxies sit at the center of a cluster. One of the things my colleagues and I are trying to do now is to look at more nearby clusters and to see, for those few galaxies that do not show this alignment, is it because they're not sitting at the center of their cluster? Are they offset somehow from the center of their cluster? And maybe that would be a clue, again, about what causes these alignments. So that's something that we're planning to do next.
I want to go into dark matter, but I don't know if this is the right time. Let me just summarize what I think I know. So you were looking at these galaxies for about 10 billion years ago, light years. When the universe was 10 billion years old, and you found an alignment, correlation between the cluster of galaxies, between the largest galaxy in the cluster and the cluster itself. Right. Am I right on this so far?
Yep. Absolutely.
Okay. Now, if we go outside the cluster, and we have a picture of the cosmic web here, did you go further into other clusters to see if they were aligned with each other, or are we looking within cluster groups? These are aligned within each other.
Good question. We were just looking at individual clusters. Are the galaxies within a cluster aligned with their host cluster? But in fact, there's been lots of work in the past. I've been working on this topic for 25 years, showing the galaxy clusters are also aligned with each other. That is, 2 neighboring galaxy clusters, both of which are elongated, tend to be elongated in the same direction. They tend to point towards each other, essentially.
And is that a cosmic web thing? Could you put that up, Carl? Do you have it up? Oh, you do. Sorry, I didn't see it. Here, let me just wang that up there. There we go. All right, so there's this thing. Let me just zoom in. This is this thing called the cosmic web. This is about the best I can do for now. These tendrils, folks, this isn't a nebula. I just want to be real clear. This is a simulation of the distribution of galaxies in the large-scale structure of the universe, and that ain't no gas cloud, folks. That is tendrils of galaxies, right, Michael?
Yep, absolutely. And dark matter and gas. Let me explain really quick. This is a computer simulation from the Illustris group, the Illustris simulations.
Great. Yeah, I've heard of it. That's awesome.
This actually shows, it's one of the biggest simulations done, right? Yep. And it actually shows a transition of a region of space. On the left side, the sort of blue and pink, is the dark matter distribution, essentially. And as you slowly go towards the right, it goes towards the more colorful material are stars and stars within galaxies. And then at the far right, the kind of orange and yellow, that's actually gas. So it's the same volume of space. We're just highlighting in this one image 3 different components that make up this cosmic
Oh, I'm
web.
glad you pointed that out because I was wondering about that. Okay. So on the left side, we're looking at mostly dark matter, some galaxies,
Right.
and on the right, we're looking at gas and galaxies.
Right. And the thing to take from this is, again, this kind of what we call filamentary structure, these kind of long tendrils, as you said, of the cosmic web. And so anything that's born within this cosmic web, we think, or many objects are influenced by it. So, for example, in the center of the image is this kind of white, big object. That's a galaxy cluster.
Similar
It's
to what we
forming in
just
this
looked at.
simulation.
Yeah.
Exactly.
And so
if you look
with-
at this picture, go ahead.
No, please finish. Go ahead.
So if you look at this picture, you see that something like this is fed along these filaments. It's fed not from every direction, but along certain preferred directions that are related to the surrounding filamentary appearance or the surrounding cosmic web. And so what I think happens is that this imprints preferred orientations of galaxy clusters and their biggest member galaxies, the ones that reside at the center, because they're born by the flow of material along these cosmic rivers, these rivers of dark matter and gas and galaxies and stars that all flow along preferred directions. I often use the analogy, I say it's like a spider web, right? And so sitting at the center is the big galaxy, that's the spider. But instead of eating other insects, it's eating other smaller galaxies. And the spider web isn't perfectly round, it's not perfectly spherical, it's elongated so that the big galaxy at the center eats other galaxies along certain preferred directions, and its orientation, because it's built up from this, reflects that orientation of the surrounding cosmic web.
Oh, wow, that's something. Now, if you run that simulation, you actually see these galaxies kind of going through the they kind of swarm, don't they? It's very active.
Absolutely.
So I guess if you look at a certain point in cosmic time, like what you're doing, then you would see these alignments, but you would also, over a long period of time, you'd see all this motion too, wouldn't you? So aren't they kind of related? And I guess, yeah, let me just stop there. Aren't they kind of related, these motions of the galaxies with their alignments? I mean, those
Absolutely.
tendrils didn't come from nowhere, right? They came from, presumably they started with the imperfections in the CMB, or the cosmic microwave background, and then grew into these structures.
Right. Well, I mean, this sort of cosmic web is a really natural development in the birth of the universe. That, as you say, there were these small fluctuations present in the early universe, and these got amplified by gravity over time. And you can show that the most natural shape or topology to come out of this is in fact a kind of filamentary structure with some voids and some two-dimensional walls. But generally, these sorts of filaments are very naturally expected. And material drains or flows along these filaments. And anything that's at the node where one or more filaments intersect, a lot of material piles up there, and you form big galaxy clusters, and you form big galaxies.
All right, good. Well, I want to get to a couple of comments here. Have any Adam Synergy is asking, have any cosmological numerical simulations looked at BCG alignments? What is that?
Well,
what are
BCG is BCG is brightest cluster galaxy. In fact, that's what we studied. The title of our paper is 10 billion years of brightest cluster galaxy alignments. And that's a really good question about simulations. There have been very few that have actually looked at the birth of BCGs, or brightest cluster galaxies specifically. And it's hard to do, right? If you look at that Illustre simulation, a big chunk of the universe, and trying to also simulate down to really fine details like individual galaxies is challenging computationally. Just this week, one of my colleagues, and I should mention my collaborators on this paper were Roberto de Propris, Malcolm Bremmer, and Stephen Phillips, all in Europe. We have another collaborator who's doing computer simulations of the birth of these giant galaxies. And in fact, their preliminary results at the moment seem to show that, in fact, just as we observe, you do see these strong galaxy alignments for the brightest members in each cluster going back to 10 billion years into the past or so. So there's at least one set of simulations that suggest that what we're seeing maybe isn't that surprising.
Okay. Well, okay, Twitch, if you're there, I've got the live chat, so leave some comments there for as well. I've got a lot here going on Facebook or YouTube. Let me look at these. Root is saying, is Tony wearing a Newcastle United football shirt? I am. Newcastle United. It doesn't matter that they've been relegated. I still wear their Go Magpies. Okay, so
I do have a question about the alignment of the cluster and the alignment of a large galaxy in respect to the smaller galaxies and the expansion of space and time and the cluster's ability to communicate with its own small parts of itself. Mm-hmm. So is there a possibility that the large galaxy at the center of the cluster is aligned with the cluster's orientation because when that galaxy formed, it was presumably the older one, and it was able to more actively communicate with the orientation of the cluster filament, whereas the smaller ones are younger, and so they might not have communicated as much since space and time had expanded?
That's a great question. I think there could be some truth to that, and in fact, there's multiple ideas for why the brightest galaxy in each cluster seems to be aligned with the cluster itself. And one could be that, it's a sort of chicken and egg question. What came first, the chicken or the egg? Well, what came first, the giant galaxy at the center or the cluster that surrounds it? And maybe, in fact, they were both being born or developing at the same time, and they influence each other in a sense. Whereas the other galaxies, yes, some of them may have formed later, but they also don't seem to be in any particularly special location. If you're sitting at the center of a massive pool of dark matter, a massive system of galaxies, that's a pretty unique place where if there are environmental influences on galaxies, they're going to be the strongest there. And so that's why these may have slowly shaped or twisted the galaxies at the center over time to reflect the surroundings, whereas other galaxies, if you're the biggest galaxy, you're just kind of sitting at the center and everything's going on around you. If you're the other galaxies, you're in this cosmic waltz. You're dancing around the center of the galaxy cluster. You're in a constant state of motion, and you presumably experience different evolutionary and dynamical processes as a result.
Okay. Let's see, a couple more. I'd like to see Tony doing the show in a Geordie accent. Lol. No way. I can't do Geordie me like. Okay. Let's see. I want to talk a little bit about dark matter. You showed some dark matter maps in there, and in one of the galaxy cluster images. A question I get a lot from viewers is, first of all, how do you know this dark matter is there? It won't interact with us. We can't see it. We can't touch it, taste it, smell it, interact with it in any way. How do you know it's there to such a great precision? I know that we look at it from things that we can see, like its gravitational effect on galaxy rotation. But how can you make these maps, and what role do they play, do you think, in these alignments?
Great question. There are different views about dark matter, right? There's a lot of evidence that something's going on. The rotation curves of galaxies, gravitational lensing, other examples that say, either we don't understand gravity or there's a lot of invisible stuff out there, right? And I'm personally a dark matter agnostic. The thing that really kind of...
What does that mean?
To me, I'm open to anything, right? Much of what we believe will be wrong in 100 years. It's the way it is. Particularly, the thing I find most compelling, the evidence for dark matter, is actually the gravitational lensing studies, because these maps that people can produce and the models that they can produce are so good they can actually predict where we should see other distorted images of fainter galaxies and things like that. And when people go and look, they're there, right? So if there's not dark matter, you need a really compelling explanation that can reproduce flat rotation curves, that can explain the gravitational lensing that we see. All these arcs and arclets that show up so beautifully in Hubble images, like the frontier fields and the clash clusters. Mm-hmm. You got to explain that somehow. And so you either have to say, we're wrong about gravity, or there's lots of invisible stuff. And again, I'm agnostic. There's a part of me that says, who said everything in the universe has to light up and become luminous? There could be lots of invisible stuff. Now, it can't be the normal stuff that makes up you and me and stars and galaxies. But, it's a strange universe. So why couldn't most of it be made of dark matter?
I know, and I want to dive into this just a little bit, and because it's an interesting topic and it's related to what you're doing, and it's also related to the frontier field. So, Carol, if you'd like to make some comments on these dark matter maps, feel free to jump in. But from what I understand, what they did with frontier fields, and probably what you've used when you said it can predict these galaxy lensing events, that what they do is they actually build models of what they think the lens looks like, and they look at it. If there were only the visible stuff, then a lens would do X. But it doesn't do X. When you actually look at the image of the galaxy cluster, you see other things. So then they start adding in other parameters to include what they think the dark matter might be and where it might be, and they build these lens models. Right, Carol? That's the way I understood it. And those models are then applied.
Well, there are many models for each cluster.
That's true. There are many models.
There are many models for each cluster, and there's a lot of variables because it not only depends, the appearance of the field with the cluster and all the background galaxies depends a lot on, redshift of all the objects that you can see. So there's a lot of geometry going on that has to be assumed. So the more information you have, the more constrained it can be. It is true that if you get a distribution of a lens that doesn't match the visible part, you have to invoke something. But there are often other indicators from different, X-ray or something like that. But I'm not an expert at the frontier fields by any stretch of the imagination.
No, I know, but you have a little.
But the idea is that you model everything you can possibly see, and you amass all the information that you have, and you put it into the model. And different groups have different ways of modeling the lens. By and large, they're in agreement, but some of these the clusters are pretty difficult.
Let me give you an example. For each of these clusters in our study, for many of them, we had the mass model from the dark matter, the gravitational lensing studies, and independently, we measured the distribution of the galaxies themselves, and we could measure the elongation of the cluster. So we had two ways to measure the cluster elongation, from the dark matter maps, and independently, from the distribution of the galaxies themselves. And they agree remarkably well. So it'd be a strange kind of coincidence if the dark matter maps were just giving you the same answer as the distribution of galaxies do. They're probably both reflecting the same underlying mass distribution.
Yeah, I get annoyed with dark matter because it won't interact with us anyway. It's hard not to get my feelings hurt, but at the same time, it's hard to ignore it, right?
Well,
I have one interesting thing on that subject. Sorry, go ahead, Carol.
Oh, I was just going to say so by and large, correct me if I'm wrong, Michael, but by and large, the frontier fields clusters are more, nobody's isolated, right? None of us are isolated, but isolated clusters. You have examples like the bullet cluster and others, where it's clear that two clusters pass through each other in a dark matter map. The two clusters pass through each other, and they're over here on the two sides, and what's left is the dark matter in the middle. So the dark matter does not always totally get dragged along with the optical cluster that we see.
Right. Yeah, that's true.
These aren't doing this. They aren't smashing into each other.
No,
that's why the frontier fields and the clash clusters are nice, stable clusters.
Okay.
And what I was going to say is I had the opportunity to go run around the Johnson Space Center not too long ago, and they have a really wonderful instrument on the ISS called the Alpha Magnetic Spectrometer 2. And they reached 1 billion interactions recently, and I talked to the chief scientist of the ISS. Now, she's not a physicist, she's a biologist, but she obviously works with the particle physicists and stuff like that. So we're going from really big to really small real quick. But essentially what she told me, the physicists that were working on it have basically narrowed down all of the interactions that they're seeing in there and eliminated all the different types of subatomic interactions that might be something else, and then they're only seeing interactions that could be dark matter interacting with, I don't want to like start throwing out particle physics terms because I'm by no means an expert, but that's kind of the general summary of what she said. Is they, similar to what you were saying, Michael, is only on a micro scale, is that we've eliminated down everything else that it could be, and then the models still seem to reflect reality. So there is this thing there that just isn't interacting with anything else, but there seems to be maybe some subatomic quantum interactions going on, as is what she was kind of talking about, that could only be dark matter. Still could.
Ideally, it would be great to detect dark matter in a laboratory someday, and that's kind of the hope, right? But, if you think about it, this was the great leap in the 80s and 90s, in particular, when astronomy led the way for trying to understand the nature of dark matter, first showing it that we thought it existed, and then, so what is it made of? And there was all these simulations like cold dark matter, right? Nobody's ever seen cold dark matter, but if you make computer simulations based on a certain properties of particles that we'll call cold dark matter, it does a remarkably good job of reproducing much of the structure that we observe in the universe, from small scales up to the largest scales. So we've never seen this cold dark matter, but if it has the properties we think, it's really good at explaining what we see.
Well, let me ask you a little bit about the some of the alignments that. So you've looked at these alignments from the distant galaxies. What do we see closer to us? What do we see with the closer, newer?
I'm glad you asked that question, because I was going to ask if these kind of alignments are seen at a lot of different redshifts.
Yeah,
they are, in fact. So,
oh, cool.
They were first established nearby, and so that's been known for half a century almost. There's a paper from 1968 where an astronomer showed that the biggest galaxies and clusters tend to share the same elongation as their host cluster. So that's pretty well established. So what we wanted to do was to say, okay, how far back in time can you see this? We believe it's established now, but when did it start? And can you look far enough back in time where you don't see these galaxy alignments anymore? That might be an important clue about how they happened, right? So if you look at nearby clusters, the Coma cluster, the Virgo cluster, you look at all these nearby galaxy clusters, you see these sorts of alignments. You don't see it in a local group because, I made the analogy before about clusters being like these cities of galaxies, and in that case, the local groups are our little tiny village, right? It doesn't have that many galaxies, doesn't have any big ellipticals, so there's no alignments or preferred orientations of galaxies in the local group, for example. But when you go to these big galaxy clusters like Coma or other ones, then you do start to see these even nearby or at low redshifts.
So we're not necessarily aligned with the Andromeda Galaxy then.
No, well, as you know, we're going to hit. But,
we're aligned into that way, yeah.
We're lined
on the collision
up.
course.
Okay. No, we're not pointing at each other or anything like that.
Okay. Okay. So these where are you planning on going next with your research? Is this it? Are you going to look at more galaxies, or are these 68 or 65 enough? Is there more Hubble data for you to go through?
No, that's the challenge. We did everything we could with the existing data that are available in the Hubble archive and everything like that, and we'd like to push it to even higher redshifts, or in other words, looking further back in time. And that's one of our goals. We have some collaborators. We're looking at things like radio galaxies and quasars at very high redshifts. Another thing we'd like to do is to say, okay, what does cause these alignments? It's one thing to say how far back in time can you see them. It's another thing to say, all right, but what's causing them? And so then we want to look at more nearby galaxy clusters where we have huge samples. There's tens of thousands and more in the Sloan Digital Sky Survey, for example. And to look at things like I was saying earlier, are those galaxies that don't show the alignment, is it because they don't reside at the center of their cluster? It's like real estate agents say everything's about location, location, location. And is that the explanation for the alignments that we see? It's only those galaxies that reside right at the heart of their parent cluster, their galaxy cluster that they reside in. are they the only ones that show the alignment? So we want to try and do some more work there too. So we have a bunch of different projects planned, plus more computer simulations. We'd really like to do some sort of state-of-the-art simulations that are able to actually watch the birth of one of these supergiant galaxies and see if we can get some better understanding of the alignments that way.
Okay. Philip W. is asking, is there a relationship between the alignments of these galaxies that you're looking at and the expansion of the universe? Do they move with the expansion, or are they independent? Any correlation between that?
No, that's a good question. I mean, in the galaxy clusters, they've stopped expanding with the universe, right? It's like the local group. The gravity in our volume of space is strong enough that it's stopped the expansion. That's why we're on a collision course with Andromeda. Gravity's bringing us together. And so in any of these galaxy clusters, their self-gravity is so great that they're no longer expanding with the expanding universe. They're held together in a compact configuration because of gravity.
Okay, yeah, the expansion of the universe is a very large-scale effect. That's why we don't see the expansion of the universe like expanding the stars within the galaxy. They're all bound gravitationally, and the same is true for why the atoms in your table don't also expand. They're bound by different forces that keep it together. This is a huge, large-scale phenomena, the expansion rate. Whatever dark energy is, it's operating on these really, really large scales. So that's pretty cool. All right. Well, Carl, do you see anything in the other platforms that we need to be making known to our guest?
Well, there seems to be our own version of the Fermi paradox when it comes to the silence on the other channels.
Okay. Yeah, I don't see anything on Twitch.
Twitch.
Where is Facebook? Let me look at Facebook. I bet there's... No, you're right. There's people who shared it and people are watching, but there's no comments. Okay. All right. So, all right. Well, let's... while we have a few minutes left, I want to talk a little bit about Lowell Observatory. You are the deputy director of science there. Give us some sense of what's going on at Lowell. That's one of my... let me just back up a minute. I do these hangouts on Wednesday nights with the guys from the Planets Foundation, and they are building. They've got these funds, these privately made funds for building telescopes for their own. And the Lowell Observatory, I'm reminded, it was a privately built observatory in its beginnings that has had a long and storied history, and so it's one of my favorite observatories. And I like to kind of it's located right in Flagstaff, Arizona, right?
Right. Yep.
And so, what are some of the things you guys are working on there? It's a ground-based observatory. I know you're using Hubble data for this study, but what other things are you doing at the observatory?
There's a lot of exciting things going on here. I mean, as you said, we have a very rich history. This is where Clyde Tombaugh discovered the planet Pluto, of course, but it's also where Vestos Slipher made really the first observations of the expanding universe. He really got the first spectra or redshifts of galaxies or nebulae, as they were known then. There's a lot of history, but it's not just about the past. We're also very much looking to the future. So we have about 15 astronomers here, all doing research. We have a 4.3-meter telescope called the Discovery Channel Telescope, which is located about an hour south of Flagstaff. I was just observing there Sunday night. And it's great. It's got a growing state-of-the-art suite of instruments. So we think Lowell's positioned really well for the future in terms of our research. We've got a really good team here doing a lot of interesting science, from solar system, comets, planets, all the way to the large-scale structure of the universe. We've got everything in between. And having our own telescope, the Discovery Channel Telescope, 4-meter telescope, is great. We've got partners who share the telescope with us from Boston University, from University of Maryland, University of Toledo, Northern Arizona University here in Flagstaff, Yale University as well. So there's a lot of exciting things going on here at the moment. And I encourage everybody to come visit. We get 100,000 visitors a year out here.
I was going to ask about that. Don't you guys do public nights too?
Wow, I didn't know it was that many people.
Yeah,
that's fantastic.
It's a beautiful campus. It's great up there.
Northern Arizona is gorgeous.
I
grew up on the East Coast. It's gorgeous out here.
Yeah, I love Arizona.
actually what we're trying to do is we get 100,000 visitors now, but we could actually accommodate more. We're just bursting at the seams. So in fact, right now we're having discussions about building a brand new visitor center out here with a planetarium,
nice.
open air theater, a lot of really amazing stuff we could do. But yeah, at the moment we get 100,000 visitors, and 6 nights a week we're open for stargazing. We've got the Clark telescope, which is the one that Percival Lowell actually built to look for map the canals of Mars. You can go see the telescope where Pluto was discovered. It's a 3-minute walk from my office here. So there's that sense of history, and we do have stargazing. We put out, you can look through those telescopes. We've got several others. We put out Dobsonians. It's a great way to spend a day with your family. And if you come here during the day to learn the history and to see all the sites, you can come back at night for the stargazing.
I highly recommend it, folks. If you're an amateur astronomer,
I'm sold. I'm getting in my car.
Yeah, you're just over there in Texas. You can drive. Yeah, so yeah, if you're an amateur astronomer, guys, you got to check it out. It really is a great place to visit.
The skies here are spectacular. You can see the Milky Way from outside my office. Right, Flagstaff was the first official international dark sky city, so we protect the dark skies out here. And it's amazing to see the number of people come up here and they've never seen the Milky Way before in their life.
Right.
It's sad, isn't it? I know.
Yeah.
But it's important.
It's 2/3 of Americans now who can't see it, right?
Yeah.
So the skies are really, really nice here. Plus, we're 90 minutes from the Grand Canyon. And, talk about spectacular views and starry skies and everything. So it's a really good place out here.
Great. Okay.
Great. We're sold. We're on our way.
So a follow-up question from Philip W. Let me get this in since we still have some time. Is there enough data so far to predict where the alignments are going, and even on a minuscule level? So you're looking, and I want to just add my own little bit to this. You're looking at the alignments as they are right now. You're finding that the largest galaxy cluster within a cluster is lined up with the cluster itself. Can you run this forward and see if this isn't just some fluke of when you're looking, some bias of like?
Good question. Probably not, right? Because again, we're looking at galaxies today, and we see the alignments, and we look back 1 billion years ago, 5 billion years ago, 10 billion years ago, and we see the same alignments. So it's been going on for a long time, for most of the history of the universe. There's a lot of other things we can look at. So if you come back in 1 billion years, and I encourage you all to do that, you'll find that the big galaxy has grown.
I'll be here.
There you go. The big galaxy has grown even bigger in size. And who knows? I mean, it's possible, for example, maybe the alignments become diluted over time in the future. If, the flow of material along the filaments diminishes, and the galaxies start to gobble up their neighbors from more random directions, maybe you weaken the alignments. And that's something we could check with computer simulations, of course, which we haven't done, and I'm just speculating. The other things that we want to look at, too, are there are other types of alignments as well. For example, there have been claims from some people that if you look at the other galaxies in the cluster, they tend to point towards the center. They have what they call radial alignments. They all point towards the big galaxy. And we haven't looked at that yet with the Hubble data. We'd like to do that as well. But some people have presented evidence that that may in fact be the case for nearby or low redshift galaxies, galaxy clusters.
Okay, Larry Keese is hi Larry, it's good to have you back. Larry Keese is asking, how many telescopes are there? I guess he's referring to Lowell. How many telescopes you got up there?
Well, it depends which ones you're counting. We've got the Discovery. There you go. We've got the Discovery Channel telescope. That's the sort of jewel in the crown. It's our 4.3 meter. It's just been in operation full time for 2 years. So it's state of the art. There's a site out here called Anderson Mesa, and we've got a 72-inch telescope out there. We've got a 41-inch telescope, a 42-inch telescope, and a 31-inch telescope out there as well. And those are used for research. And then here, we also have an interferometer that we share with the Navy. So you can, I don't know if people know about interferometry, you link together multiple telescopes, and it acts like one giant telescope to give you exquisite resolution. And so we've got one of those out here as well. You might have seen in the last week, Alma presented the first images of I guess it was Betelgeuse, right? Mm-hmm. Incredible what you can do with interferometry to resolve stars. And we've got an interferometer out here. And then here on Mars Hill, which is where my office is located and where the astronomers work most days, we've got the Clark telescope that Percival Lowell built. We've got another smaller telescope And then we've got the Pluto telescope up the hill as well.
So you really don't have many then, really. Okay, so not so much. Sorry about that.
It's nice because one of the good things about being an astronomer at Lowell is you can get access to a fair bit of telescope time, which is great for doing projects that you couldn't do anywhere else, where you need many nights or you need observations over 10 years or 20 years. There's a project that's been going on here for 30 years that you couldn't do anywhere else. And that's one of the beauties of a independent observatory like this.
Wow. Well, I'll ask about that one in a minute if we have time. Alexander Reynders is asking, though, or Reynders, I hope I'm getting it right, guy. What is the alignment of the galaxy clusters to each other? So you looked at the galaxies within the cluster alignment, but are the clusters aligned with each other?
Well, we didn't look at it in this case, but they absolutely are. I and many other people have looked at this in the past. If you could put up the image again of the cosmic web, Carl.
Sure thing.
So if you look along those filaments, embedded within them are groups and clusters of galaxies. And we find when we measure the orientations of neighboring clusters that they have a strong tendency to point towards each other because they're all oriented along the direction of the filament. So any clusters that were born within the same filament generally tend to share that same orientation of the filament, and therefore they tend to point towards each other. And this has been known again for, the first paper that did this was by a Swiss astronomer named Bruno Bingley in 1982. So it's been known for 3 decades, basically.
Right. Okay.
And we didn't do this with the Hubble data because although we have 65 galaxy clusters that we looked at, they're at much greater distances, and so they're very sparse around the sky. So we don't find many neighbors around each of those particular clusters that would allow us to do a similar study. Someday we'd like to do that.
Yeah, Alexander's also asking, are these alignments observed in any Z distances? And we just talked about that a little bit, Alexander. He was saying that the nearby galaxies have been known for a while to have alignments. So
right.
You just
I was going to say that it's also possible with W1st, which will be very wide field, that several clusters will be able to be observed together.
Right.
That's going to take a while to build that telescope.
Okay.
Webb will be great too because the further back the time you look, like for the most distant clusters in our sample, we were actually measuring the infrared light from them because as you go to higher redshifts, visible light gets shifted into the infrared, and so James Webb will allow us to get nice images of some of the most distant galaxy clusters.
Yeah. So we got 2 conversations going at once here now. Cosmic Stardust now wants to know, what does the Navy use an interferometer for?
Several different things.
Is it classified? You can't talk about it. You can tell us, but you'd have to kill us, that kind of thing?
Yeah.
No, but I mean, some of it is looking at things like binary stars and trying to, in the old days, right, the Navy was all about timekeeping and all about, guidance systems in a sense. And so there's the using the celestial sphere as a GPS system is important too.
Yeah, Toxic Vamp, JWST hype. You better believe it, buddy. It's going to be awesome. So just get ready. Okay, beginning. Oh, wait, hang on here. I'm just. Let's see. What could make the universe expand? That's from Shayura, and there's been several responses that I've made videos on this, and that's true. But the short answer is what currently the big answer is that they think it's something called dark energy, which is causing this expansion, because not only is it expanding the universe, it's also accelerating. And yes, there's been plenty of videos made about that. We don't have time to go into it right now, but that is the short answer for that. And and okay, well, I guess that is it. We are out of time. I'm gonna stop right there. I want to thank all of you for watching. I want to thank my guest, Dr. Michael West. He's the Deputy Director of Science at Lowell Observatory, which is in Flagstaff. And if you ever get the chance, head over there and check it out. It's a good public place to visit. If you are going to the Grand Canyon, you may as well stop by and see it as well. Or if you're going to Lowell, you may as well stop and see the Grand Canyon. I mean, what the heck?
It's on the way.
Yeah, it's on the way. So, so yeah, definitely.
Planetary science and astrophysics.
That's right. It's all there. Okay, well, so I'm getting comments. Larry wants me to ask you back. Will you come back, Michael? Will you come back?
Anytime, I'd be happy to. It was fun.
This has been a great topic. I want to thank you for being such a great guest. Usually we have 2 or 3. You did all the heavy lifting yourself.
Yeah,
so.
Really. Thank you so much.
Yeah, they left it to me.
Yeah, well,
I enjoy it.
Well, thank you.
You had more fun than they did.
Absolutely.
That's right. Thank you.
Thanks so much for doing it. We really appreciate it.
That's right. Okay, folks. Well, we are done with this one. I want to thank you all for watching. Next week on Thursday, I will be back at 3 p.m. Eastern Time to watch for the Footsteps to Mars Hangout, where we are going to be talking about the long-term health hazards of being on Mars and some of the planets in our solar system. For example, what are the health effects of going to Mars? Is Mars toxic? Are we gonna get like some kind of is it good for us or is it bad for us? Or what do we have to worry about health-wise going to Mars? So we're going to talk about that next week, and also our Astro Coffee Hangout will be back the following week after that, which we are still working on. I want to remind everybody that if you want to know what hangouts are coming up, go to deepastronomy.com/hangouts, and there's a calendar there with all of the events on it, what's coming up and when. So please check them out. Carol, do we know what we're doing next to Astro Coffee, or is it a little too early to tell?
We're negotiating.
We're still in the contract. Okay,
yes.
Okay, good. So tune in 2 weeks for our next Astro Coffee Hangout. I want to thank my guest, Dr. Michael West, Dr. Carol Christian, also Carl Clark. Thank you guys for doing a great hangout. We got another one under our belts. Thank you all so much for watching. Have a happy 4th of July if you're in the U.S. If not, then have a happy 4th of July anyway. Yeah. All right.
Exactly. Right.
Okay. Well, all right. So thank you all for watching. And as always, keep
looking up.